Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Rabbi shrahli sadri wa yassir li amri wa hlul 'uqdatam min lisani yafqahu qawli. I continue chapter 5.3, inverse of linear transformation. Objectives of this section. At the end of this section, you will be able to determine if linear transformations T is invertible and to find the inverse of a linear transformation T. Okay, before we start with the inverse of linear transformation, let's recall that we have learned in a previous section, about kernel and range. So given a T be a linear transformation, so kernel T is a set. This set, kernel T is a subspace or subset of a domain, of domain, this V. First, you should write a homogeneous system, TV equals to 0 vector. Form a homogeneous system, and then you reduce to augmented matrix. Reduce this homogeneous system, you transform to augmented matrix and then reduce it to ref and then solve. Solve for variable, whatever variable that involved in the system. And then so this working, is similar to a null space A. So null space A, we use AX equals to 0 vector. So nullity T is equals to nullity A. For range T, this is a set of range T. TV, you should write, you should begin with TV equals to AV. So V here is a vector. Sometimes we use TX. TX equals to AX. Similar, right? It's the same. Then after that, you find a standard matrix A. You should find a standard matrix A from the defined transformation. After that, reduce that matrix to ref, and then you take the corresponding pivot column of A. So the working is similar to column space A, and rank T is equals to rank A. Now we start with inverse transformation. A linear transformation T V maps to W is invertible if there exists a unique function T inverse equals to W maps to V, where T inverse TV equals to T inverse W equals to V, and T inverse W equals to TV equals to W. So W is image, and then V is the object. So W in a codomain, V in a domain, right? But for inverse function, so W becomes domain of inverse T, and V becomes codomain for inverse T. In theorem, in terms of theorem, let T R to the N maps to R to N be a linear transformation where Tx equals to Ax. So the following conditions are equivalent. So this one comes the property of this linear transformation. T is invertible. If T be a linear transformation, so when if this T is invertible, so T is 1 to 1 and onto, and A is invertible, determinant of A not equals to 0. So when we work with when we want to work of inverse of transformation, so we should work with the standard matrix A. If the standard matrix A invertible, so T inverse exists. So let's do moreover, T inverse X equals to A inverse X vector. This one. The relationship between T inverse and A inverse. This one. Alright. let's do example. For a following linear transformation, determine whether T inverse exists. If so, and then find T inverse. Alright, to check whether T inverse exists, we should deal with the standard matrix A. Okay, get the determinant of standard matrix A. If the determinant is not equal to 0, so inverse of A exists, therefore inverse of T also exists. Okay, let's start. So we given question A, given this transformation of T and defined as this. So to firstly, you should form a standard matrix A. Okay, get the standard matrix A from this equation, the transformation equation. Okay, so the first row is for first component. All right, the second row is for the second component. So just take the coefficient, right? Then after that, find the determinant of this matrix. And you find the determinant, it is equals to 5, so not equal to 0. So if determinant not equal to 0, that means matrix A is invertible. In other words, A inverse exists. So therefore, T inverse also exists, right? So then if A inverse exists, so therefore you should find A inverse. Okay, find the A inverse. Right, this is matrix 2 by 2. So using formula of 2 by 2. Alright, so this the final the result of A inverse. Then remember this relationship T inverse x vector equals to A inverse x vector. So using this relationship, we have this equation T inverse. So x vector here is x and y. Okay, the variable involved in this function is x and y. So it equals to A inverse x and y. Okay, xy. The x vector is xy. You plug in A inverse and then you multiply these two matrices. So the end result is the inverse of T. Okay. Next question. Do next question. This one R cube to R cube. R cube maps to R cube. Okay, the given transformation, this equation, all right? So there are three components. So for 3 components and 3 variables, so therefore the standard matrix is of size 3 by 3. So for size 3 by 3 is, so the working is more longer than size matrix of size 2 by 2. Okay, to find determinant of A, all right, you have you can use series, and here I use series. You also can use cofactor expansion, right, to get the determinant of A. Here determinant of A is equals to 3, so this one is not equal to 0. So conclusion for this work, right, you should write the conclusion for this work. So therefore, matrix A inverse exists. Thus, T inverse exists. Okay, this all right. Okay, conclusion for this determinant is a must. You must write this conclusion. Okay, why T inverse exists? This one, determine whether T inverse exists. Okay, why T inverse exists? T inverse exists because A inverse exists. So that's why this conclusion is very important to write. So after that, find A inverse. So this one, 3 by 3 matrix. So 3 by 3 matrix, you can use arrow or using adjoint method. Okay, you can use adjoint method, but adjoint method it involves cofactor matrix. So make sure you get the correct cofactor matrix. All right. Here I use arrow. Right? Arrow. This is matrix A, and this is matrix identity. Then you should rearrange. Okay, rearrange the end result. You should get the left hand side matrix identity. So the right hand side is the inverse of matrix A. Okay, using arrow. Okay, using arrow, you get this one. So therefore, my All right, the inverse, A inverse is this matrix, and then apply this equation, T inverse X equals to A inverse X vector. Right here, X vector is A, B, C, okay, the three components, and then A inverse, we plug in this A inverse, so X vector also A, B, C, so you multiply to these two matrices, all right, so and then this end result is the matrix of T inverse. Okay, next example. All right, this one is 2 by 2. So the standard matrix A, first you should get the standard matrix A. Here, the first component gives first row, all right, second component for second row. Just take the coefficients, right? And then find the determinant of A. Here, this is 2 by 2. So 2 by 2 formula to find the determinant is very easy. So it is equals to -1 is not equal to 0. So when determinant is not equal to 0, that means A inverse exists. Thus, T inverse also exists. Okay, so therefore, find the A inverse using the formula of inverse matrix 2 by 2. You get this. After that, apply the equation of relation T inverse and A inverse. T inverse is okay, vector X is xy, then equals to A inverse multiply with vector X, here X and Y2. Okay, then multiply these two matrices, you get this end result. This is the matrix for T inverse. The next one, question D and E. So this is for you to try to get the T inverse. First, you determine whether T inverse exists by using determinant of a standard matrix A. And then if the determinant is not equal to 0, so you should make a conclusion that A inverse exists, thus T inverse also exists. So after that, find the A inverse and then get the T inverse. Okay, so good luck for these two questions. Okay, I hope you will do. Test yourself, right? So this is the end of chapter 5. So for exercise, please do test A and test C. Okay, test A, page 262, test C, page 264. And we will discuss in tutorial class. So for that, I end the class with tasbih kifarah and surah wal-as. Okay, Assalamualaikum warahmatullahi wabarakatuh.